Hello everyone. Today I want to talk about how to create a current source in bipolar realm, how to generate current sources, which are very important basic part of all designs and very susceptible ones. They define the current in the circuit, so if we design a bad current source, we would have lots of problem. And when we tape out a chip and it come back, it wouldn't work, or it would work based on lots of variation, like temperature, noise, and other stuff. And so it is very important to uh, design a very robust current source in both CMOS and bipolar, but maybe in bipolar is more accuracy is needed. And nowadays, because of BiCMOS technology, which is kind of become cheaper and cheaper, and even there are open source BiCMOS PDK out there by IHH. You can find it easily on the internet if you search open source open source BiCMOS. We will find it, and you can use it actually. And there are also soft open source softwares that will help you to design, and you can use BiCMOS basically these days. And BiCMOS is very popular. One reason is we know that BJTs, bipolar junction transistors, are they have a better performance. They are faster. They have higher bandwidths and everything. But the problem with them, and it's very kind of um, desirable for an analog designer, but the problem is they are not, because of their the way that they should be biased and the way that they should work. They are not very popular. They are not popular at all in in digital designs and between digital designers. So one reason that IC design engineers shifted to CMOS was because we always like to have all digital and analog on one die, and the performance are the performance of BJTs are very limited by are limited for digital design. So enough with the introduction, just go through the circuit design part. So in CMOS, when we design a current source, sometimes we use something like this, and we add a bias at the gate of the transistor, but it is not possible to do this in bipolar. The reason is, if you do this, for example, here, I added like I generate the bias over here in the base of this transistor, and we know that IC, this is IC, would be equal to IS, and VB, I will call it VB, which is this is VB over VT. The problem here is because the relation between the base bias and current is exponential. If you have a very small variation over here, it changed the current drastically. If I draw the VPE over, or in this case VP VB over IC. It is something like this. It is very like a crazy type of behavior, and this is why we like it as an analog designer. It would have a better gain, better frequency response performance, and for example, the GM over ID is better usually, and you can have with less current you would have a better GM, then you would have a better frequency response and everything, and it's better gain, everything. So one way to address this problem, and it's a very smart and easy way, is so the easy way is not this one, but I like to mention this, is to add a resistor over here, and then you will have, so you can define IE, or okay, which is kind of equal to IC by VB. This is VB or called RE. Here you can see if RE is sorry, if RE is huge, so then the dependency of current of the current source over the VBE would be limited, and you can suppress that phenomenon. You can define it by RE, for example, and VB. There are other ways to bias it, but this is one way that which is more robust. There is a problem here that this start our conversation and discussion over here is for having very robust current, the RE should be huge. Depend on your supply, as RE would have effect on the DC of the circuit. You might have a overhead problem, or a headroom problem, sorry, so it would limit your headroom. As I mentioned, you should increase RE, and this limits your headroom. So we can use this as a current source, but with limitation. Also, there is another limitation. We always know that we can like define current source by ideal current source and the R out of the current source. This is a non-ideal current source, the real one that we always deal with, and we very appreciate if the R out is high, because when it's high, so this is, for example, V over I of this current source. We like to have always have a constant current which is not depend on the voltage of the current source, but we do not have that, and we will have something like that when our out is smaller, and we will have something I'm gonna use something more desirable if our out is huge, because when signal is going through the circuit and it changed the voltage, for example, in this node, because our out the current is changing, and when current is changing, the specification of circuit is changing. This is philosophy behind it, that we always like current sources with huge R out. you can find the following equation in all of the textbook about bipolar transistor, that we can define R out of this current source as RO 1 plus RGM RE. Yeah, we can define it like this. And if I'm not sure if I'm correct, but it will be something like this. It's like this, okay. And also the RS of the transistor with effect and maybe kind of a let's say decrease the R out. The RS is the resistors RS or RB of the BGT would decrease this value. But the problem, as you can see, if you want to have R out, huge R off, also you should increase RE, and then you will have additional problem of the headroom, or headroom problem caused by additional reason. So I was trying to explain something else over here, and I kind of forgot. Oh, okay. But beside using like equation and everything, I always like to inspect circuits, and one way, sorry. So one way to like find out if this circuit has, by adding an RE at its emitter, would have a higher R out, is just to look at it differently, kind of. So I add R out here, and if you add RO here, sorry, and if you add when you are going to measure the R out, you add the voltage source here, and you measure V out over I. This is V out. So how we can find out by adding RE we have a higher R out? This is a very nice question to ask without using equation and everything. You will see if you increase the voltage over here through the R out, the voltage over here will increase. So this increase in the voltage in a small signal kind of generate a current by the transistor that that is not working in favor of I. So you would have something like GM minus GM BPE created by this effect, and as you can see, the current of the voltage source will be reduced by this phenomena. And this means that using this equation and Ohm law, this means you would have a larger R out. So by inspection you can find out this. This is very kind of awesome way to look at this. So we do not like this circuit. This is clear. So another way to generate a current source is by using a current mirror. And if you have if you have a defined current source or current reference using band caps and everything, you can generate a current which is not dependent on the behavior that I explained before. So you can have like a current and which has a relation with the current reference in some way, but there is a difference between this circuit and CMOS. Is you would have you know, in CMOS you do not have this phenomena, there no current at the gate, and this is the basic reason that we like CMOS in digital. But here this phenomena cause a little bit inaccuracy between the reference current here and the output current. I just wanted to mention this. So you can have a R out here, which is R out is equal to RO of the transistor, let's say Q2, and without adding any RE that reduce your headroom, and it with affects stuff like swing and other stuff in the or common mode range if you use this current source in, for example, a differential pair. So yeah, you can just copy the current, and it is important to the matching in BJT will be defined by IS2 and IS1. If IS2 and IS1 are equal to each other, so they are matched, and you should also be careful about layout consideration to define this correctly if you want a good match. But how to increase the R out of, because RO might be not kind of enough, and we know in BiCMOS and lower node BiCMOS the RO of the transistor is not very high, because VA, the early voltage, is smaller, and most definitely in RF, the BGT designed for RF, because they kind of reduce the area of the base to remove the CB parasitic effect, so they kind of let's say decrease the VA, and early voltage early effect will be kind of dominant in RF, so having high RO is not very easy to achieve. So I like to go to another page if I be able. So there are ways to do this. One way is to like so one way to do it is to use like what we always do in CMOS, but this is actually the more amazing part of this tutorial. So we can do something like this, and add like another BJT, so here, and you will see that we increase the R out by the factor of beta. So the R out will be beta, which is kind of a huge, and beta is the difference, like the ratio between IC and IB, and so it's in high orders, so you can increase the R out by factor beta, which is kind of amazing. Another way to, and there is a kind of a nice thing to mention here. You might at the beginning of this tutorial I mentioned that this is not a good thing to do, to add a to add a voltage bias at the base of the BJTs because of the reason that I mentioned. But the kind of amazing thing here is you didn't do that by using this configuration, because still VBE is not defined by this guy, and this node could be flexible to define VBE in the way that it wouldn't be kind of affected by the effect of IS and other stuff in the circuit. So I forgot to mention this, that if you have a BJT like this, one thing that is happening is as the IS has a relation with area of the size of the transistor and with the temperature, so it changed drastically by the when you bias this, so IC will flow through the BJT and it generated some sort of heat, and then this changed IS, and then when IS is increasing, so IC increase too, and you generate a loop that kind of increase IC in a way that you cannot stop, and kind of reduce and limit the functionality of the BJTs. This is the basic reason that we do not put voltage at the base, a constant voltage, and we define the IC not by VBE or not by the voltage at the base, but by a reference, in this case this guy, or at the other case by RE or stuff like that. And you can see we didn't define the VB of this transistor IC by a constant voltage, because this voltage could be flexible. And I just wanna show you another configuration here. So another way to generate current source or current mirror with a high output resistance is like what we do in CMOS, but there is a very fun difference here. So these are grounds, and so you add this. But if you do the equation, you will see that in this case the R out is RO, it's beta over 2 RO, so you reduce it by factor 2. And why this is happening is amazing. This is very important to notice here, that because we have in CMOS we do not have a current in the base, but in BJT we do have this, and kind of the signal goes through here. If I show you the equal small signal would be the Rm of this transistor, or 1 over Gm, the Rm of this guy, and then R pi, Rm, V pi, and then GMV pi, and R out. This is very fun thing here, and I very like it. The reason that you have beta over 2 here is that you have this current, small signal current source here, that kind of add a current at the output. We know when we have more current, so we have less R out. So the reason is that for example, in CMOS we do not have that. In CMOS this does not exist, and what we have here is R out only. Or in the other configuration that I showed you, if I delete this, in the other configuration that I show you, which was this one, forget VCCs, and just also in this configuration you do not have this phenomena RM and everything, and the equivalent of this circuit would be I don't know where to. The equivalent will be, I think I should delete this. I'm gonna show you the equivalent. So the equivalent will be, sorry if I'm not very fast. So equivalent will be this guy. The current source RO, and this one is like in we do not have this in, so we have RM of this one. It is connected here to RPi. So the R out here is but you see that because the both side of this part is terminated by ground, so you do not have VPi here, so you do not have this, and you do not have a current that kind of flow through this transistor to reduce the R out. You only have the R out. This is why you have beta RO. I want to show you another way that is even not reliable on the small signal model, and you can find out this easily. And I showed that when I was talking about GM boosting and regulated cascade in CMOS. We draw the circuit again, just a current mirror, and these are grounds. So I always like to do this, so I think when this is going up, so this go up, it's a common base, but as it's CMOS, as it's BJT, we will have another path through VPi. Here it will be like a VPi, RPi, VPi, and the RM, as I show you, RM of this guy and also RM of this guy, and the RPi of this guy. So when this goes up, this goes up and this goes up, so it will be up, 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 down, and down. So you do not have an increase in the voltage. So by Ohm law, when you have a decrease in a resistance, sorry, if you have a decrease in decrease in voltage, you have a decrease in a resistance. This is one way that you can look at that. This path kind of reduce the R out, but it is important that the red one and the green one are not equal, because this path is very high gain, but this path is not very high gain because of RMs. So you know that when this one is going down, it will be very small, and here also very small, but you know that R out is increasing, but not that much. Or another way to look at it is the way that I told you about, and I mentioned earlier, is you just draw RO. You know this one is increasing, so this one also has RO. So when voltage here is increasing, this one is increasing too, so you have a current that is not in favor of the current of the voltage source that you added here to measure the output resistance. Also, one nice thing to mention about this, you have the same phenomenon in BJTs, is to understand that this is not very low voltage configuration, because you have VBE here, another VBE here, so 2 VBE, and here always will be VBE. So the if you have a swing here, or not let's say swing, if you have a like if it is a differential pair here, for example, so it would be limited by VBE here, and also like VCE set, and here VBE, not VCE set. So it's like just some let's say the typical numbers. So it's 0.7 here, 0.2 here, and 0.7 here. So you would have 1.6 volt limitation in your common mode range. Something you might don't like, or I don't know. So one way to make this low voltage is just to add remove this one and add this configuration, and we know how to do that in CMOS. I just want to mention two small other things and finish this video. I know it was long and maybe I was not very fluent in explaining it, but you can ask me questions by sending an email to me, and also I will add some links in the description that you can refer to. Some of the concepts that I explain here will be found there easily, and also besides that I add some other links that are not references but could help you to understand BJTs more fluently and more comprehensively. Another thing that I want to mention is the famous Wilson configuration. I just want to mention this one to just for inspection of the behavior. Sorry about this. So let's draw it. So the famous Wilson that even we might see this in CMOS. One thing that I want to see here is that R out increased by this configuration. This is the only way. How to do that? I use my method. I see if this goes up, this goes up. Change color. I see. I will say if this goes up. So when this goes up, but the RO here wouldn't let that the phenomena that I mentioned to happen, so the signal come back and and then go down and everything, and this one goes down too. So we can see that the phenomena, it wouldn't happen, and still the R out is beta RO. This was one thing to mention at the end. Another thing is just the Whittler configuration that is kind of very famous. And in Whittler, one thing that you can do if you have a matching problem is to add a resistor here. And then you can easily copy the signal called R1, R2, and even you can copy it here. You can see that for example, IC1, IC2 relation is dependent of the VBEs and IS of the transistors, and you can easily copy this thing without the matching considerations, but still you would have the ratio between them, and you can copy them, reduce them, or without use the change the sizing of the transistors, and then just the ratio R2, R3. But they have a reverse relation between R2 and R1 and IC2 and IC1. So by just using KVL KCL, you can define this, and this is good for define matching and everything. I do not remember anything else to mention. You can listen, because it was very long and maybe I speak slow and not very fluent. You can speed up the speed of the YouTube option to listen to that. If you have a question, I kind of do not respond to comments because I forget, but you can send me emails, and if you search my name, you can easily find me on internet and my email. I received some emails from people asking about different things for different video that I published before. I hope you understand the whole thing, and you just can easily reach to book references, textbooks, papers, other tutorials on the internet to help you to understand BJTs better. In some university, I know that they do not teach BJTs. It could be a good start if you are going to be a BiCMOS designer, to understand BJT's basics using these tutorials. Or also you can start designing using open source software and open source BiCMOS PDKs available on internet by IGH. I'm going to mention their name. IGH is a German semiconductor company based on Frankfurt in Germany. They have a GitHub. You can just download their PDK, and there are tutorials there how to integrate the PDK to your open source software. And just use it as a designer, or if you are a student, use it for your homeworks and stuff. Also, I hope I can find a tutorial that I had about how to simulate BJTs in SPICE, in HSPICE, without using PDK, just to define everything, like the small signal models and everything, even the parasitics and everything on a HSPICE file, and just simulate your desired circuit, just for a start, not for design, just to maybe for your homework, or if you have an idea or something, using just non-real model, which is not a model actually, is a small signal configuration that you define to that could help you to understand BJT's behavior and even the parasitics effect more deeply.